Yeah, welcome back everyone. In the previous video, we showed how to derive the two equations, two second order differential equations that govern the motion of a spring pendulum, and I rewrote them here nicely so you can see them. We note that theta double dot is second order and del double dot is second order, and then we have dels and thetas and mass and lengths and gravitational constants. And the other video describes exactly how to get to this point, so I'll leave a link for the first part in the description below. So basically you solve using ODE45 and then you can plot the results in Matlab using the following steps. So first thing we need to do is we'll discuss how to plug into ODE45, which is a Matlab function for solving ordinary differential equations. And this function actually it's used to solve first order ordinary differential equations. So we'll have to use a little trick to reduce the order of set of second order differential equations from second order to first order in order to plug it into ODE45. Then I'll show you how to write a function handle. ODE45, you have to write a function handle. You don't just plug it into your main code. And then we'll show how to modify the existing code from the previous video just to make it nice. Make the variables nice to plug into the function handle. And then we'll write the main code of the simulation file, which basically it just calls the ODE45, and then we'll plot the results from that, and then plot and view results. So it's not really difficult. It's just basically reducing the order of the second order differential equations and plugging into ODE45. Okay, we'll get started. Okay, one common trick for reducing the order of second order differential equations is to define a column vector z that contains your variables. So this is the column vector with theta, theta dot, del, and del dot. And if we take the time derivative of z, we get z dot, or we differentiate everything piece by piece to get theta dot, theta double dot, del dot, and del double dot. And we notice that we can substitute in here. Theta dot is nothing more than z of 2, or the second row of the column of the original column vector. And the same is the case for the third row of the z dot. The third row of the derivative vector is the same as the fourth row of the original vector. So now we can solve our equations and reduce them and use ODE45 with this simple trick, because we are solving now for z dot, which is the first derivative of z. And basically we're going to be using some matrix math where z dot is going to be solved for using ODE45. Okay, like we said in the previous video, we can develop the equations symbolically in MATLAB. So I'll run this code to get equation 1 and equation 2. But now we want it to be in a nice vector format. So with respect to the variables, so we want to get theta double dot and del double dot, each of these on a left-hand side of the equation, so we can use MATLAB solve function. So let's say equation 1a is equal to, we're gonna solve it just equation 1. Let's make this thing equation 1 and we're going to solve that one for theta double dot, and let's see how that looks. Oh wait, I think I need to use parentheses or not really. Let's see. Okay, there might be no reason to use the quotation, doesn't make a difference. Anyway, I'll keep them in there. And then equation 2a, we'll call it the same thing, except we'll solve equation 2 for del double dot. And we'll change that to equation 2a. And there's no need to see this. And there is no need anymore to see this one. So now we've solved our differential equations and we've gotten theta double dot to the left hand side of each. And now to make it even easier, let's use the Z1, Z2, Z3, and Z4 notation that we talked about in the previous video. So we can say some new sims, Z1, Z2, Z3, and Z4. So Z1, Z2, and Z4, and I'll have to just come up with another name for the equation. We'll call it FY1, where we substitute equation 1a, and for the current variables can use this tilde notation to make it accept the matrix. Theta, theta dot, del dot with Z1, Z2, Z3, and Z4. Okay, close that. And let's see how this one looks. Okay, we're getting an error here. Z2. Oh, I think I can't use commas here. Yeah, there's no use of commas. That's right. Okay. Okay, run that. Okay, so that's FY1. We're going to use that to plug into our function handle ODE45. We'll do the same for FY2. And just as a reminder, Fy1 was the second derivative of theta, or theta double dot, and Fy2 is the second derivative of del double dot. As you remember, in this previous step, we brought the theta double dot and del double dot to the left hand side, and now we're just replacing theta, theta dot, del dot with Z1, Z2, Z3, and Z4. And I just need to change this to equation 2a, and everything else should be the same. Okay, so now we can go into our ODE45 function and copy and paste these directly. Okay, the next step is now to create a ODE function handle for the spring pendulum. And I just created a new M file and called it my ODE function. So we have to use the same naming. So function, we'll call it Z dot, as we said previously. And we call it the same name, which is my ODE45 function, and then you're gonna pass two parameters. You use this tilde notation to to pass the time variable, and then z, which is the column vector we showed previously. And now the global variables are gonna be mass, spring constant, length, and gravitational constant. And then the column vector z dot, or the derivative of z, is going to be made up of the four components that we showed previously. So the first one is z of 2 followed by a colon. The second one is going to be a copy paste from that previous function or the previous script. So let's open that here, this one, symbolic, and we'll run it at path. It's gonna be this term here, copy, paste. So this one we said previously is the same as theta dot, and this is theta double dot. We need to use, open this, open and close parentheses on each of these Z1, Z2, Z3, and Z4. Okay, that's the second term. Third term, as we showed previously, it's Z of 4, or del dot, and del double dot is this term here that we symbolically derived. Copy paste, and we'll add parentheses for each of the Z terms. Okay, and that's the function handle. We'll close, and then we'll call this function handle from our main simulation. So let's see. Okay, now here we're in the main file, which is where we call our ODE function, ODE45, using the function handle. So we can start by clearing the screen and clear all variables, and let's run that. So we cleaned up our workspace, and we'll define our global symbols here, which are M, K, L, and G. Global, mass, spring constant, L, and gravity. And then we will define these. So let's say the mass is 1 kilogram. The spring constant is going to be 25 newtons per meter. The length of the pendulum, let's say 1 meter. And gravitational constant, 9.8 meters per second. And now we need to define the initial conditions of theta, theta dot, del, and del dot. So theta, let's say we are at some theta of pi over 8. And theta dot, initial condition, well, it's not going to be rotating because someone is just going to hold the spring pendulum at a position. And then del, let's say he stretches it, or whoever the person holding it stretches it by 25%, so 0.25 of a meter. And finally, del dot, it's not moving in the normal direction because it's being held by a person. And let's put here an underscore. So we put these initial values in a matrix or in a vector, column vector. theta 0 and theta dot 0 del 0 del dot and 0. Okay, now we will set up a time, well, basically discretizing time. So we'll say t initial is gonna be 0 seconds, and t final, we can let this run for 10 seconds, and now we need an increment, so let's say 0.05 seconds, and now n is going to be the number between number of increments final minus initial divided by dt. Now we can use the linspace function to get the time span, which is linspace, and we put in the final, initial, and the number, so as it's showing here in the suggestion. Final, initial, and number of increments, and next we're going to run the ODE45. Basically we have a time and a z. It's going to return these two parameters. We're going to call it just ODE45, and we have to use our function handle at this point with an @ symbol. So we called our function handle ODE45 function, comma. So here it is. If you didn't see it, we have to use that naming right there. And we have to plug in the time span and the initial conditions, initial values. And let's run that to see the results. Okay, as we expected, we have our Z matrix is made up of 4 columns, and each column represents one of our variables. So our variables are theta, theta dot, del, and del dot. So now let's go ahead and assign theta, theta dot, del, and del dot to these values. Theta equals z, comma 1. Theta dot equals z 2. So that double colon just means give me all the rows, and 3 is column 3. So and then we need to say 4. So del without the dot and del dot. So 1, 2, 3, and 4. So that's theta, theta dot, del, and del dot. Okay, next let's change it to, because we're going to animate the pendulum and look at how it moves in the XY plane. So now we need to go back to Cartesian coordinates. So to go back to Cartesian coordinates, we will need to multiply the length plus the del, length plus del, times the sine theta, because it's taken from the vertical, to get x, and times the cosine theta, because it's taken from the horizontal, to get y. So let's, I think we'll need a for loop, right? Well, okay, let's initiate x and y just using zeros. Zeros of n comma 1 and y equals zeros of n comma 1. Basically, I have now created two column vectors that are 200 rows long and one column, and they are filled with zeros. So now in a for loop, I will assign each value. So for I from 1 to n, for I equals 1 to n. Now we can use x of I equals, length is always, it's a constant, so we have it L, but now we need to go to the ith parameter of del, or ith row of del, times the sine of the ith row of theta, and that'll give me the x, and the y will be the same except times the cos theta. Change this to cos, and let's change that to y, and we say here end. Okay, now we're gonna plot it. So we can say figure 1 will plot x comma y comma, plot it in red color, and let's give it a title, the x y plot of a spring motion or spring pendulum animation. That's our title. X label, let's say, just call it X position. X plus, and the Y label will be Y position. Okay, let's define the minimum and max values of x. So let's go from negative 1.5 to positive 1.5 in the x. And the y minimum, negative 3 to, let's say, just plus 1, because it's not going to go above 1, but it might go below 1 because it has a spring. Okay, now we'll define the axis, which takes vector, because Matlab did everything in terms of vectors. X min, X max, Y min, Y max. And now we will hold on. Okay, now here's how we're going to animate. We're going to use a for loop for I equals the length of time, because we're going to increment in time. If I is greater than 1, then I will delete call it P, and then delete L telling it to delete the previous, and now P defining what is P. It's just gonna draw a point, plot X of I, Y of I. That's why we said if I is greater than 1, because if it equals 1, P is not yet defined. So that helps me draw the point. We need to hold on. Now we use the quiver function for L. Here's the quiver function for L. Quiver basically draws a vector from the points you enter. So X, Y, and U, V. So our X, Y is always 0, 0. And U, V is X of I and Y of I. So that's the quiver function. It draws a vector from 0, 0 to the point. And we need to hold on again. And we say draw now. Axis is X min, X max, Y min, and Y max. And we will pause for the length of dt, for the time span of dt, and end our loop. Okay, let's run it and see if it works. We're missing something here. Oh, I have these backwards, I think. Yeah, I do. Should be like that. Oh no, it should be like this. This is the argument. And this is a vector. It should be like this. Oh, I did the same here, didn't I? Okay. So this should be the vector. And it's fed as a function. Okay, more errors. What's this error? Undefined function or variable x max. Let's see. X min, x max. X max. Okay, P is undefined. Okay, I was able to track down the reason for the error. It was because I didn't put a 1 to the length of T here in I, which made the I enter in probably as 0 or wherever Matlab starts, maybe 1, and it's trying to delete the P, but there's no P. So now we can run it. Okay, looks like I need to put a negative sign to get my Y, because Y needs to point downwards and not upwards. So let's kill it. Control C and CLC. Close this. And let's put a negative sign here. And let's check out what our pendulum looks like now. Okay, there's your pendulum, and that's how you animate the spring pendulum using Matlab. And maybe you can get a little fancy with this pendulum, but I just drew the crudest one that came to mind. And I guess the 10 seconds finished. And maybe we could change the initial conditions and see what happens. So let's say that we don't have any angle, and that the pendulum is just held straight up and down by 0.25. So as expected, it's just going to keep bobbing up and down and not moving. That's one way to validate it. You could also calculate the kinetic energy and the potential energy, and the total energy should stay the same throughout the whole process. Or you could calculate the energy in the initial condition and make sure that it stays the same throughout the whole process. The energy in the initial condition, since it still is zero kinetic and all potential energy, so you can calculate the gravitational and the spring energy to give you the potential energy. So a lot of things you can do with this. Let's change the angle again and see what happens. Let's stretch it out by 75%, and let's give it an angle of, I don't know, negative pi over 8. Start it from the other side and see what happens. So it's starting from here and it's stretched out a little bit more, so you get this pattern drawn by Matlab. Okay, and I hope you enjoyed this video. Like and subscribe if you want to see more. Thank you. Take care.